Hello together to the next statistics lecture at the Jade Hochschule. First of all, since we have also exchange students and we will do some calculations also in Excel, because I want to motivate you to use this tool. So I just looked up, there is a function translator, so where you can put in the German function and translate it into the English version. There you can just click on it, and there is also a function translator as an add-in within Excel. And here I gave you the links, and this looks like, where we are. There. So this is the Excel function translator where you can put in here the formula, or from Microsoft you have here also an add-in of a function translator, and here it is explained how you can install it. Okay, so then we will go on with our short revision. Actually, you gave me also the feedback that your last statistics lecture is maybe 2 or 3 years in the past, and yeah, therefore that we all know what we are talking about, I make this short revision today. So the last time we talked about conditional probability, and yeah, therefore I want to give you today a short overview what we are talking about, what is how is a random variable defined, what do we understand by probability distributions, and so on. And while we are doing this, we will also do some questions I will pose you, and we will solve them together today. So first of all, random variable. What do we have? A random variable x is some mapping from the sample space, and this sample space is just our events, rolling a dice 1, 2, 5, 4, 3, 4, 5, 6, or that something happens, like some crazy guy from Russia just begins a war or something like this. So this is a sample space omega, and from this sample space omega, the random variable x is mapping into the real numbers r. So there we have some countability then, and this then means that actually if we take then not the sample space as a whole, but only one elementary event within this sample space, that this maps on some specific number xi, and then we say the probability of this event ai is just the probability of x being xi, which we get from this mapping on xi, and this is then known as the probability of some event. And pi is then the probability that the random variable equals to some outcome xi, not more and not less. And there we distinguish a little bit, because we say that this random variable, this is actually written in capital letters. This I gave you also here. But the realization, the small x I, this we write down in lowercase letters. So there you have conceptually always to distinguish between these two, the random variable and the realization of this random variable. And so then we can, every possible event in a random experiment can then be expressed in a random variable. And this is always, if you're doing mathematics or statistics, we create something like a common language that we all know what we are talking about, and we do not have always to explain what we are talking about. And here is my example, which I already posed, is that rolling a dice has then the sample space 1, 2, 3, 4, 5, 6, and the realization could be then that you just roll with your dice the number 5. And then a very hard question is, what is then, if this is a perfect dice, what is then the probability that x is smaller than 5? Could you help me? I know this is a really hard question. Sample space is 1, 2, 3, 4, 5, 6. And what is then the probability that the number we have rolled is smaller than 5? And we have perfect dice. Yes, of course, you're right. So just then we have the events. P of x is 4, P of x equals 3, P of x equals 2, P of x equals 1. These are all the events which are smaller than 5. Everything is 1 over 6, and so we got 4 over 6 2/3, or 66%. Well, I think you all know this, but just as a first explanation of a random variable. And I think it is always good if we make examples and not talking only about the theoretical part of these explanations. Okay, then of course we have to distinguish between discrete random variables and continuous random variables. Discrete random variables, there we have something like rolling a dice, because then we have 1, 2, 3, 4, 5, 6, and this is a discrete. Every event is one natural number, 1, 2, 3, 4, 5, 6. But discrete can be also realizations which are countably but infinite. And there you can take, for example, flipping a coin always once in a row. So flipping a coin once, twice, 3 times, 4 times, and so on. And well, in the end, you can do it. You can go on and flip always your coin, but you still can count it. And then you have 1, 2, 3, 4, 5, all these events of flipping a coin. And this would be then a discrete variable with countably infinite realizations. And then, of course, we have also continuous random variables, where we say that the realization is in between some interval on the real numbers. So maybe the realization is in the interval, let's say, a quarter past 12 and a quarter to 1. So this is 30 minutes. And let's say that maybe a bus is stopping within this time interval. Well, maybe you have heard this in school, that the real numbers you cannot count. So you don't have a mapping from the natural numbers onto the real numbers because, we have infinitely more real numbers, so to speak, a bit less speaking, infinitely more real numbers than we have natural numbers. But then if you have these continuous variables, then we can also calculate with the probability density and so on, which comes later on. So this just to be complete, that we have to distinguish between discrete and continuous random variables. Then here, what is the difference and what is common between discrete and random variables? Well, we have the probability, or to be specific, the probability mass function, that the probability of some specific event, some specific realization, this is given by the probability of the event. But what would be if you have a continuous random variable? Let's say this bus stopping within 30 minutes. What is then the probability if you take a continuous variable of p x equals xi, or in our bus stops at some specific time? Let's say specific time, an example 12:34. So p of x equals 12:34. If you have this continuous variable, what is then the probability of such an event? Didn't you do this in your statistics class? Then the probability is just zero because we have overcountably events within this continuous interval. And so we cannot say that some specific event has any probability. And therefore, we introduce the probability density function. Again, let's say here this normal distribution, which looks like this, but you cannot interpret this point here on the vertical axis as the probability of this event. You can only interpret probabilities in some interval here. So this can then be interpreted as a probability, and therefore then we have these cumulative distribution functions. And if we take the discrete case, then it is just summing up all our probabilities. This we have done here. In our example, we had these four probabilities of equal always 1/6, and we summed it up. 4 times 1/6 is just 4/6. But in the continuous case, we have to take the interval. So the probability to be less than specific numbers is the area below the probability function. So probability can be interpreted as the area below the density function. And then, of course, we already had done it when we calculated some averages and so on, that the sum over the event times its probability is our expected value. And if we go to a continuous variable, then again we have to take the integral, let me say, over the whole sample space. Generally, then when we have the mapping into the real number from minus infinity to plus infinity times our event is the expected value, and the variance is of course defined at the squared distance times the specific probability in the discrete case, and summing up we get the variance, and within a continuous variable we again have to take the integral over the squared distance respectively to the expected value. Well, I think this you all of you have already seen, but yeah, this I want also a small revision on this, that we keep this in mind when we later on doing calculations with this. And then we should also know if we doing some calculations with the variance and with the expected value, that of course if we do not take any random variable but only a constant, then of course the expected value of a constant is just the constant itself. And we have of course no variation, no volatility around a constant, and therefore the variance of a constant equals 0. Well, and then we can manipulate our random variable, and manipulating, oh, this should be a capital X here. And this should also be a capital X. That if we multiply our random variable with a constant number, that then we can just take these constant number out of the expectation operator. Well, let's do it just for the once for the discrete case. Here, if we take this formula, then we have E of x equals sum over xi pi, and then of course we have E of a x equals sum a xi pi, and since this is a linear operator, these summation, then we can take out the a and write a times sum times sum over xi pi, and this again is our expected value of x. But of course, if we take the variance of a random variable multiplied by a constant. And this we will also need later on. And this is also very important that you keep this in mind when we come from some general distribution and then we want to normalize it, or if we come from some general from some general normal distribution and we want to come to the standard normal distribution. And if we look this also up within here, then of course we have here our xi, but we have here the square sign, and this just means that of course we had that the expected value, there we have just this linear transformation, that in this case we can say variance of a times x means the sum of a xi minus a mu. This a mu comes from here because this also means that we have a mu squared pi equals, and then we take a squared times xi minus mu squared pi, and then the a we can put in front of the summation. A squared sum xi minus my pi. Okay, but I think this is not really difficult, and if we take this together, then we really can say that the expected value operator is just a linear operator. So expected value operator is a linear operator. But of course, the variance is not a linear operator. So if we take this here, that the variance of a constant is 0, and this one, that if we multiply the random variable with a constant, then we get squared the constant outside the variance operator, then this together means if we make a linear transformation of our random variable, and this we are doing really often in statistics, because we need these transformations to to handle the our problems in an easier way. Then we just get only a squared outside the variance operator. Okay, then what is statistics then all about? And these are the famous Kolmogorov axioms, that at first we have our sample space, and within our sample space we say that every event has maybe only a probability of 0, but it cannot be negative. Every event has to be a non-zero, has to be 0 or a non-zero probability. This is the first axiom. And then, we normalize all this to 100%. And then this means if we take all events of our sample space and want to know what is the probability of X being all possible events in our sample space, that this is just 1. And axiom 3 means that if we have disjoint events A and B, that means if we take A and B simultaneously, if we take these events together, and if this is the empty set, then the unification of events A and B is just the sum of both probabilities. Okay, and if we take these axioms, then we can derive from these axioms some rules how we can calculate then all these probabilities, and especially at first, of course, these two events A and B, they in general do not have to be disjoint events, and this then means that we take the sum of both probabilities of event A and B, and we have to subtract the probability that both events happens simultaneously. Because in this case, if we take any possible events, then this could be different from the empty set. So possibly, because in general, this could be different from the empty set. Second rule, if we say I want to know what is the probability of A and B does not happen, then we have the second rule that this is the probability that B happens minus the probability that A and B happens together. And the third rule, I think this is the simplest rule that just if we take the complementary event, and here we just put it that we write here some bar on our letter. So the probability of A bar is just 100% minus the event itself. But I also think that all these rules are known to you. And then this we had in the end from the last lecture that we also can then define the conditional probability of A given that B has happened or B happens simultaneously, that we can say this is just the probability that A and B happens together divided by the probability of B, and from this and our rules and axioms from statistics, we can derive Bayes' theorem we had the last time, that we have P of A conditional B means that is equal to B probability of B conditional to A times probability A over probability B. And in order, to keep this in mind, we will do here some calculations and doing some examples. So let's say that P of A is given with 50%, P of B is given with 30%, and that both events happens together. P of A and B is just 20%. So first of all, what is then the probability of P A together with B? Can you help me? If you just go to the slide, then I think you just can look it up. Oh, if we go here, then this would be just rule 1, P of A plus P of B minus P of A and B. So P of A plus P of B minus P A B. Inserting this is then 50% plus 30% minus 20% equals 60%. If we go to B, B of A, conditional B, you can also give me just the numbers. This is just using the formula. Yes, I think these are right, so I will write it down. This is then P of A and B, and so in order to show it to all of you over P of B, so it is just this formula. Up. P of B 0.2 tips, no, so not 10%. How did you calculate 10%? Rule 2 over 0.3, because then, of course, we have 2/3, right? Is 66%, okay? Yep. So maybe you just made a little mistake. This could happen. Then let's take C. P of not A and B. This looks complicated, but it is not. Because what can we do? Again, here we just can take rule 3 and the complementary event. The probability is 1 minus the event itself. Well, we have here maybe a bit complicated event, but we have given the probability of this event. So this is just 1 minus P of A and B, and then we get 1 minus 0.2, and this is 80%. And the last one, this is just P A without B, and there we have again rule 2, so P of B minus P of A and P, and therefore, oh, so now I see 10%. So you really have to, I think this, maybe it's not a mistake you made, but here, these are different signs. So if you have this and if you have the backslash, these are different signs. So this is the conditional probability, and this is A without B. I think, yeah. So it is not a mistake. You just looked at it. Maybe it is also a bit small that you couldn't really see it. So no problem, of course. Thank you. Okay, so I think just this yeah, the main things in statistics, and this you should really you should being able to do these simple calculations, because at the one point or at the another point in the following lectures we will need these simple calculations from the introductory courses of statistics. Okay, then if we have independent events, then of course it doesn't matter if something else happens, and then this just means that P of A conditional B is equals P of A, and P of B conditional A equals probability of B itself. And if we take this with our rules and axioms together, then of course we can calculate the probability of A and B equals just that we multiply the single probabilities. And this is just if you flip a coin, then to get the number, then and flip your coin twice, then it's just 1/2 at the first event, and the second flipping is statistically independent, and then you just calculate 1/2 by a 1/2 is 1/4. And we take some examples for these statistically independent events. They are really at the Bodensee in Constance, there is a casino, and this really happened in 1988. That in 1988, really 9 times the event 0 or 3 really occurred. And if always standing at the roulette table and in every event that these are statistically independent, we then can calculate the probability. And what do we have to do if we are playing roulette? I think you all know this game. What is the probability playing roulette that we have the event 0 or 3? How many numbers do we have at a roulette table? Hmm? No one of you played roulette? We have this wheel. And how many numbers around here? No one? Oh, 36. Great. So we have here from 1 to 36 plus the 0, and so we have 37 numbers. And what is then if we start our wheel only once? What is the probability that we get the event 0 or 3? So 37 numbers. Also, we think about a perfect wheel here, like we think about a perfect dice. then every number has the same probability. Yes, of course. So P is then 2 over 37. And what is then the probability if this happens 3 or 0 9 times in a row? So P of x element of 0, 3, 9 times in a row. If we take this, if all these events are statistically independent, then this is our formula, which we have to use. A and B, so A is the event 03 in the first time, B is the event 03 in the second time. Hmm? Well, if we take only 2 times, then it would be 2 over 37 times 2 over 37. But we have it 9 times in a row, so 2 over 37 and this 9 times, and then this equals 2 over 37 to the power of 9. Well, and now I take again my Excel file because I don't want to use the calculator. So we have here 2 over 37, and this, the probability is that this to the power of 9. And then you see that is a really, really rare event which we had there in 1988, because the probability is then what to the 10 minus 12. So this is then, what was it? 4 times 10 to the power of minus 12. Or how many guys do we have today here? 7. With me, we are 8. Though we can pose the question, what is the probability that out of our sample of 8 people, 2 of us has on the same day in a year the birthday? Or what I have posed here as a question, what is the minimum number of students in a class that the probability of this event that 2 guys have their birthday on the same day is at minimum 50%. What do you think? How many guys do we need? Is it our number 8 today? Did we already reached that the probability is 50%? Just have a guess. How many guys do we need? What do you think? If you guess, there is no wrong or right. What do you think? Just guess, please. because I'm already talking 5 hours today, or 4 hours today. 182, okay. So you just say 365 guys, and therefore you just take half of it. Anyone else of you have a guess? I want to get 2 other guesses. So this is just the first guess, and well, maybe the explanation is I just take 365 divided by 2, and then this would be the probability. Well, of course, yeah, this is your idea. I thought so. I ask, did you need more or less? Because I say 2 and also 1 is not the very surprisingly not the right answer. But anyhow, you just guess, and there is no right or wrong. Of course, sorry. Did you think that you need more or less? Hmm? Anybody else? Okay, then we start and we try to analyze this. And of course, we assume that every birthday is independent from one person, is independent from the event that another person has at some specific day, his birthday. So first of all, we have to know, if we just say this number isn't known, and the number of students. Let's say if n is 2, how many possibilities do we have at which days these guys have their birthday? So the first student has how many possibilities? Yes, of course. And the second, of course, also 365. And then, of course, the possible events is just 365 times 365 if we have 2 students, because the first one has at January 1st, then we go through it 1 times 365. Then the first student has his birthday on the 2nd of January, again 365. So we have to sum up 365 times 365, and then we get that we have to multiply 365 by 365. So then, how many events, how many possibilities do we have if we have n students? That is then not 365 squared, but yes, 365 to the power of n possible distributions of birthdays. Yes, and now we do not ask what is then the possibility that 2 of them have at the same day their birthdays, but we just take one student and we ask how many possible days are left that the second guy has not at the same day his birthday. And this is only 364. If the first student has at some specific day his birthday, then the second student has only 364 possibilities left. Then the second student has only 364. My pen isn't working. There it is back. Okay. Oh. 364 possibilities left. Yeah, and the third student, of course, 363, and so on. So then, if we ask which possibilities are left that we do not have two students having their birthdays at the same day, then we have 365 times 364 times 365 minus n minus 1. Possibilities that no students have at the same day their birthday. So the probability that two students have at the same day their birthday is then, and there we take again the formula from the complementary event. Is just 1 minus 365, 364 times, and so on, 365 minus n minus 1 over 365 to the power of n. And this then we equal to 50%. Well, unfortunately, there we have of course, no analytical solution for this. And then, well, we just can again ask Excel to solve this problem. And then we go in here and let's start. Here we see it. Let's say here our number of students. So, and we start just with, let's say we go up to 30 people or a bit more. This is our number of students. And then, of course, we need how to calculate 365 times 364 and so on. Then we start with 365 and equals 365 minus 2 minus 1 and then we go down here. Oh, what did I wrong in my formula? B7. Oh, I think I can do it easier. So 365. Oops, no, this one minus 1. This is the easy way. So, and then we have to calculate 365 times 364 and so on. So this equals then this is product of 365 times 364, and again we have to take a dollar sign in front of this 6 in order to fix it, like in the summation. And this we put down. So this would be the numbers for the possibilities not to have the birthday at the same day. And then, of course, we have to calculate 1 minus this number over 365 up power to the numbers of our students. And here we have 2. And then we go on. And then we see here that at the number of 23 guys, we have the probability that 2 guys in the room has with probability 50% at the same day their birthday. I think the result is a little bit surprising because, of course, your first guess that you just take 365 divided by 2. This is a reasonable guess, but if you start to think about a little bit more about this question, then you end up that you need only 23 guys, and today we are 8, so our probability is that 2 of us have at the same day the birthday is 7.5%. So then we need 23 students. And this is also some example how we calculate with events which are statistically independent. So, and then the last formal part which we have today is the so-called total probability. And this then means, again, if we could divide our sample space in k disjoint, again, this means statistically independent elementary events, then we can calculate the probability that an event B consisting of all these elementary events is just the sum over the probability, the conditional probability that that B and one elementary event AI happens times the probability of AI, and we have to sum all this up. And in order to handle this, we will also do some simple examples. So what's time? Okay. So every day a small village is visited by a postman, and if he is in good mood, he will be in time. You will get your letter in time with probability 90%, and if he is in bad mood and he is late with probability 40%. And we just say this guy on average will be in good mood 7 out of 10 days. What is then the probability that our funny postman is late? So if we want to calculate this probability, P of postman is late with the total probability. How can we construct this probability? Yep. So here we have the conditional probabilities, and A is then to be in good mood or in bad mood. These are our two elementary events. And then we have, this is postman is late, conditional, good mood. What else do we have? Times the probability to be in good mood plus P of postman is late and he is conditional in bad mood times P of bad mood. And now I think you can go on, or? What is this probability? Take another color. Well, if you just read the example. Every day in a small village, the postman visits this village, and then if he is in a good mood, he will be in time with probability 90%. Yes, they are great. Then just the complementary event is 10%. 1 minus 90%. Postman is late. If in bad mood, then this we directly have. This is 40, of course. And then what is the probability to be in good mood? 70. And then the complementary event in bad mood is 30. Great. And if we take this together, then we have 0.07, 7% plus 0.12, and this is 90%. So I think it's not too complicated, but if you have such an example, then just go through it and take your time, and then I think you can make it to the solution. And another example, which I want, oh, where is it? Just wanted to calculate. There it is. And to end this, then we want to combine these total probabilities and Bayes' theorem together. And this is maybe also an example if you take the vaccination or if you take the tests on corona. And then we all know that our tests on corona, they yeah, they are not 100% appropriate, that if you are tested positive, that you are really tested positive, or the other way around. There is also still some probability if you make the test and this is negative, that you nevertheless that you have corona. And this is then, of course, the question which we really need. What is then the probability? Let's say in this example here, if we are testing for some illness, the test is positive, but it is not 100% accurate. What is the probability that I'm really ill? And this is, of course, a very important question. And here, because then you will see when we calculate the numbers, that this is really very important if we have a rare illness, because then the probabilities are very small, and then especially the conditional probabilities are very sensitive. You will see in a minute. And therefore, I took this example with a rare illness, because corona is, of course, not a rare illness. That we say event A is that our patient is, let's take black again, that our patient is ill, and B is the probability that that our test is positive. We have a really rare illness, so only 1 promille probability that out of some sample of, let's say, 10,000 people or so is is really ill. Now we are testing our 10,000 guys. And from some surveys, we know that our test has an accuracy of 98%. And at the first look, this looks really high, at a really high number. But what we want to know is if some specific guy gets his test in the morning and sees these two red lines and say, so am I ill or am I not ill? And from this survey, we also know that in 3% of all cases, we have a positive test, but we have the complementary event that this guy is not ill. And now we want to see what we want to calculate. Our test is positive. What is the probability that I am by myself are really ill? Again, just have a guess. If we take these numbers, 98% accuracy, very rare. Illness of only 1 per mil, and 3% fails positive. Just have a guess. Is it around 98%? Is it around 90%? Only 10%? What do you think? Again, just have a guess. No one? Around 90 still. Okay, good guess. So, then let's start with, at first, our total probability, I think we start. So, P of B is P of BA times P of A plus, again, like in the postman example, P of B not A times P of not A. And what we want to know is, I have a positive test. This is my condition that I'm ill. So what I want to know is P of I am ill, event A, given B, my test is positive. So this is I'm ill, and this is test positive. Well, and there we have Bayes' law. We can say that this is P of B conditional A times P of A over P of B. But P of B we can calculate from the total probability. Well, and now we just put in the numbers. P of B conditional A is 0.98 times P of A 0.1%. So it is 0.001. Okay? Yes. So divided by P of BA times P of A. This we already have. 0.98 times 0.001 plus P of B not A is 0.03 times P of not A, complementary event. So what we not need is P of not A. We know P of A is 0.001. Yes, and this is then 0.999. So, then you can also calculate it. I will do it again in Excel. So what did we had? We had 0.98. We need 0.001. We need 0.03. And we need 1 minus, equals 1 minus 0.001. And then first P of A, P of BA times P of A is this times this, and we need P of B not A times P of not A is this times this. Then we sum it up, this plus this, and in the end we have to divide this by this number. Is this divided by this number? And here we are. Our result is very surprisingly, I think, 3.2%. And this you really have to keep in mind if we are dealing with conditional probabilities, and especially if we deal with very small probabilities of an event. And here we have this rare probability, and this unfortunately then means if we have a test with 98% accuracy and 3% fails positive, then actually this is not a very good test, because if then as a specific person have my positive test result, then I can only say that with 3.2% probability I'm really ill. And this is, I think, quite surprisingly a very low probability. And if you have these very rare illnesses, then you need really very accurate tests. Okay. Yeah, we have only 5 minutes left, because then I also wanted to start today with the distributions, but then to complete our first introductory overview, we take this to the next week, where we look at some very important distributions. There we start with the binomial distributions, then we look on the uniform distribution, and of course we have a look on the normal distributions, and then we will end our overview and introduction. And then we will start with significance and estimators and so on. Okay. Where is my mouse? There.